We left off yesterday in analyzing a set of spectra. By the way, I don't know that I've addressed this. One spectrum, plural spectra, which I think is like, is there a comparison for singular suffix plural suffix It's curriculum, curricula. I don't think there is a data and datum. I think it'd be more closely related to dice and die. Several dice, one singular die, I think is what it is. Curriculum and curricula, I think, is a better example. Singular curriculum, plural curricula. Spectrum, spectra, and here we were analyzing the NMR and IR spectra for a compound. Now, a challenge that this gives us, we weren't given a chemical formula. So to build a structure from nothing but spectra can be really hard. For one, if there's a halogen present, I might see the halogen in the CX bond absorption range of the IR, but also a lot of other things absorb in that same range, and it can be really challenging to know if I actually have a halogen bond. Halogens don't show up in the proton NMR because they're not protons. Halogens don't show up in the carbon NMR because they're not carbons. Halogens do show up in the mass spec, and so we'll talk about analyzing mass spec today and how to determine whether we have a bromine or a chlorine halogen. But without a chemical formula, it can be really hard to know if there are oxygens or not, nitrogens or not, halogens or not. How many carbons will I have? Well, carbon NMR can help with that. Except carbon NMR can't always help super well with that because I can't integrate carbon NMR. So if I have two carbons that are identical to each other and give the same carbon NMR signal, I can't integrate it to know that there are two there. And not all carbon NMR signals give the same height. So it's really hard to know how many carbons I have in carbon NMR. Just how many types of carbons I have in carbon NMR. Without a chemical formula, this can be close to impossible. On your unit test this weekend, you will be given a chemical formula, an IR spectrum, and an NMR spectrum. And your job will be to derive the structure. It's not impossible. It's doable, especially with a chemical formula. And we're going to do a more challenging example of it right now without a chemical formula. We already had analyzed the IR here, and we felt with confidence that there was a CO double bond that was not from a carboxylic acid. We also felt with confidence that there was sp3CH bonding. That was all that we were confident about, but we were questioning whether there was NH, but it was lacking some corresponding peaks, questioning if there was sp2CH, but there was lacking some corresponding CC double bonds, questioning if there was aldehyde, because there is a corresponding CO double bond, but not a very obvious twin peaks of the CH. We looked at the proton NMR, and we felt confident that there is no aldehyde. You guys remember that this is the abbreviation for aldehyde, right? Not trying to trick you, trying to expose you to all the different ways that we can abbreviate these things. I once looked at an MCAT study guide question, and it said, in the structure, and then it showed this, and it was like, what is this meaning? And I was like, I had never even seen it presented that way. So I want you guys to see all of the different ways it can be presented. Proton NMR tells us there is no aldehyde. Can someone remind us why the proton NMR confirmed that? That would be IR. And we actually felt like the IR, we weren't sure if there were twin peaks. Good. No signal beyond 4.5, let alone a signal at 9 to 10. No evidence of an aldehyde. Our IR left us wondering then, do I have a ketone and potentially an ether, because it does look like I have a CO single bond, but we agreed that identifying a CO single bond can be a challenge because there's a lot of other things going on. We recognized that CO single bonds up above tend to take the shape of a very strong and somewhat broad signal, because we see with our two aldehydes at the top of that page, there is no CO single bond and there is no strong broad absorption. Broad is not, just a little bit wider, not really broad. There's no strong absorption in that 1,000 to 1,300 range, but then down here, there's a lot of absorption in that 1,000 to 1,300 range. So maybe this is a CO single bond, and maybe that's what we're seeing in our IR spectrum as well. But then we said, well, I said, the proton NMR confirms that it's an ester and not a combination of a ketone and an ether. Can you guys reiterate how I felt confident that it was not a ketone plus an ether, but it was instead an ester? How did I leverage the NMR in combination with what I already learned from the IR to feel confident that there is an ester? Ester does not show up somewhere specific on the chemical shift. Ketone does not show up somewhere specific. Ether does not show up somewhere specific. So it's not that I'm looking at the NMR and saying, oh, because the signal is here, it confirms it's an ester. We can do that with things like the aldehyde, the carboxylic acid, the aromatic ring. But there's no place where I can say, oh, because it's there, it's an ester. Okay, I'll stop talking. Your turn. How did I leverage NMR in correlation with what I knew from IR to predict this? Evelyn.
Was it because there wasn't like those two signals that you mentioned, they weren't like next to each other because there wasn't two next to an L?
Good. If there's an ether, both of the hydrogen signals next to the oxygen should show up in roughly the same region. They should show up farther left because they're both next to the oxygen. An ester has signals next to an oxygen and a signal next to a carbonyl, which do show up in different regions. So the ester doesn't have a signal that shows up in a single spot, but an ester has an oxygen adjacent group and a carbonyl adjacent group, and those show up in different chemical shifts. Whereas the ketone has two carbonyl adjacent groups, an ether has two oxygen adjacent groups, and I'm not seeing evidence of two oxygen adjacent, two carbonyl adjacent. I'm seeing evidence of one oxygen adjacent, one carbonyl adjacent. What's a carbonyl? CO double bond. Does that really prove that I have an ester? Absolutely not. It doesn't, because I could have a ketone and an ether in which the carbon or carbons between them have no hydrogens, And so in this case, I have a carbonyl adjacent and I have an oxygen adjacent, but we have to do some guess and check. And right now the evidence is leaning towards guess that there's an guess that there's an ester and confirm that first. If I can't confirm that there's an ester structure, then maybe I'll come back to thinking about a ketone and ether where whatever is between them limits how many signals I would see. This is really a challenge. You guys recognize that this is a challenge? To take data and have to say, I don't know, but I think it might be this. A little bit of guess and check is okay. Take the evidence that you see presented and take it out further. If we look at the carbon NMR, and I'm not asking you guys to be experts on the carbon NMR because I am not quite confident that I'm going to even put any questions on your exams related to the carbon NMR. But in the carbon NMR, we can see that carbonyl carbons show up in the high hundreds, low 200s. An interesting feature that we can see, aldehydes and ketone carbons show up further left than ester carbons, which show up further left than amide carbons. So the fact that the ester carbon sits right here in the middle of this range, around 180, actually does something to confirm the carbon NMR, which has a signal around 180, probably being an ester and not a ketone. Then we have this signal around 60. 60, we said, is the functional group adjacent. Or I guess, yeah, I did phrase it here as heteroatom attached, but I probably would have been better to call it adjacent to a functional group. What I don't actually show on this correlation table for carbon NMR is where a carbon would show up if it is adjacent to a carbonyl carbon, because just like a hydrogen gets shifted further left, man, I got to think about which way you see it. Just because a hydrogen adjacent to a carbonyl shows up further left, a carbon attached to a carbonyl should show up further left, but not as far left as a carbon bonded directly to an oxygen, just like hydrogens show up even further left when they're bonded nearer to an oxygen. Again, proton correlation table. Hydrogens closer to that heteroatom show up further left. Hydrogens closer to a carbonyl show up further right, which is why that structure is laid out the way that it is, as a reminder to you. So I think that this carbon NMR is actually confirming that I have carbon by an oxygen, and that's showing up around 60 ppm. And then I have a carbon by a carbonyl, and that's showing up around 40 ppm. I'm not seeing evidence of two carbons adjacent to carbonyls or two carbons adjacent to oxygens, which proton NMR, we said maybe there's a way I could still have a ketone and an ether and not have hydrogens that are in between that would give me these duplicate 2 carbonyl hydrogens, 2 oxygen hydrogens. Carbon NMR says that's not the case. I don't have that many carbon systems going on. I've got one that's next to an oxygen. I've got one that's next to a carbonyl. And then carbon NMR says, I've got at least 3 greater than or equal to 3 carbons that are alkane-ish. And those are showing up in this low frequency range, 20 to 30 ppm. And I say at least 3 because I'm not confident that it is just 3. I suspect there might be 2 methyl groups that are identical to each other in this structure. The reason I think that is because of the proton NMR. I've got a 9H region, or at least that is the best that I could integrate this to. You can actually see that there looks to be multiple signals going on around 1 ppm, multiple signals that are just flush against each other and just barely overlapping. So instead of being able to get the integration of one set and the other, it seems like the integrations of both signals have just combined to look like 9H. A 9H group in the proton NMR would indicate 3 CH3s, a tert-butyl group. But those would all be symmetric to each other. Those would all give one signal, and 3 CH3s connected at a central carbon. That carbon can't have any can't have any hydrogens on it if it also is going to connect to the carbon chain. So that would be a 9H singlet, and this does not look like a 9H singlet. So I think it might be a CH3 with 2 6Hs. A CH3 with 1 6H, which is a CH3 with 2 identical CH3s. But that would mean 2 identical carbons, and that would mean one of these 3 signals is actually 2 carbons and not 1, but carbon NMR doesn't consistently give a height. Carbon NMR can't be integrated, so carbon NMR just tells me how many types of carbons I have and not necessarily how many exact carbons I have. Fun. We're loving it. Okay, so I'm going to come back to the proton NMR, and we're going to use the integrations, splitting patterns, and chemical shifts to try and build a structure. All right, I'm going to call our signals A, 2H triplet. Would you guys all agree? Just past 4 ppm. 2H looks like it's a triplet. B is a 2H multiplet. So I'm just going to label that as M. That's showing up around 2.4 ppm. Signal C is a 1H. This also looks like a multiplet, around 1.6 ppm. And then signal D, which is shown as 9H. But again, as we said, I think that this might actually be 2 different signals overlapping. I don't think that it's 3 CH3s identical to each other. And you're okay with it not being 3 CH3s? Because if it were, if this is 3 CH3 groups all connected at a central carbon, then the rest of the structure has to be bonded here. There's got to be other stuff going on. Maybe it connects to the carbonyl. Maybe it connects to the oxygen. But this carbon of the tert-butyl group would have no hydrogens on it. And if it has no hydrogens on it, then all 9 of these protons show up as a singlet.
Could it be 3 CH3s connected to 3 different carbons?
It could be. If you look at the signals, the more I look at it, I feel like I'm looking at a doublet on the right and a triplet on the left that are just butted up against each other.
So you're saying two CH3s to one carbon and one CH3 to a separate carbon?
I think there's two identical CH3s and one separate CH3, but that's hard to know.
We're saying it'd be a singlet because they're not unique hydrogens?
We're saying it'd be a 9H singlet because they're all identical and they have 0 neighboring hydrogens.
And that's based on the carbon?
Yeah, remember, these hydrogens, their neighbors are on the adjacent carbon. Hydrogen, carbon, carbon. How many hydrogens on their neighboring carbon? 0, because the rest of the molecule has to be attached. So these would all show up as a singlet. So tert-butyl, out. So we have to figure out something else. Then I'm going to say if this is one CH3 somewhere in the molecule and two different CH3s somewhere else in the molecule. Are you guys okay with, I'm just brainstorming here and I don't know what the rest of the structure looks like, but I'm saying maybe they're just connected by the rest of the structure somehow. Okay, well, what about this 6H? If they are connected identically and they're connected by this carbon, how many hydrogens at this carbon? So what signal would that give? How many peaks would that give to this signal? 2 peaks. So this would give a 6H doublet, and this would get a 3H.
Wouldn't it be 7 peaks?
Oh, no, the 1H here
Yeah.
would have 7 peaks. But the 6H
Oh, the 6H would be a double.
would be a doublet. I was talking to Saray in lab about this yesterday. Could you imagine if I showed up to Saray's house and I said, wow, you look like you have 5 neighbors just by walking into his house? How can I walk into someone's house and figure out how many neighbors they have? That's weird, right? When you look at the signal from these identical methyl groups, you learn that they have a neighbor without looking at the signal from the neighbor. Looking at their signal, you know how many neighbors they have. That's the weirdest part. And so if I went to Saray's house and I said, wow, your front door really makes it look like you have 5 neighbors. How is that distributed? Then Saray could say, well, I have 3 neighbors over there and 2 neighbors over there. That's a family of 2 and that's a family of 3. Or actually, I've got 3 neighbors. There's 2 neighbors over there and 2 neighbors over there and 1 neighbor that way. There's different ways you can get 5 neighbors, but if this is our setup, those 6 hydrogens have 1 neighbor, so their signal becomes a doublet. This CH3, well, it depends. Is it bonded next to a 1H? Or is it bonded next to a CH2? Or is it not bonded next to anything? This could be a singlet, it could be a doublet, it could be a triplet. Right now, we don't really know. So I'm going to leave this in parentheses with a big question mark over it. And I'm not necessarily confirming the 2 CH3s on the right either, but we're just brainstorming right now. All right, let's look back at some of our other ones because I think we can confirm them a little bit better. Around 4 ppm, I have a 2H triplet. So that's going to be a CH2 in my structure. Because of its chemical shift, I feel very confident that one side of it is an oxygen. Especially since I believe that there is an ester in this structure. I don't think it's a ketone. I know it's not an aldehyde. I know it's not a carboxylic acid. I'm pretty sure it's an ester from the IR. NMR is not telling me it's an ester. IR is telling me that it might be an ester. Because of its chemical shift, I believe it's next to the oxygen of the ester. And because of its splitting pattern, here's the deal. I'm actually going to switch this up. I'm going to draw this in orange. And I'm going to draw what I think is happening around its environment in green. The signal is coming from the CH2. But the way its signal is presented is because it's next to an oxygen and, what do you think?
Another CH2.
Why?
Because it has to have two neighbors because it's a triplet, and the other 2H is closest to it.
Good,
So it's second closest to the oxygen.
good. I think that this signal comes from hydrogens bonded to the oxygen of the ester because of its chemical shift being at 4 ppm. I think this signal has a CH2 because it is a triplet splitting pattern, so the number of neighbors must be 2. If it were a quartet, the number of neighbors would be 3, and it would have to be next to a CH3. Let's look at our next signal. Signal B. Here's a 2H multiplet around 2.4 ppm. What would make the signal show up around 2.4? Proximity to a functional group. I worry, sorry. I don't know the structure. We're learning it together. I'm getting a little worried. That's okay. Proximity to a functional group, not a functional group as electronegative as just oxygen. Something less electronegative. Since we believe we have an ester, the only possibility there would be the carbonyl. And we know that this carbonyl is an ester. How do we know that? Again, the combination of IR and NMR is suggesting to us that we have an ester. To its right, I don't know. How many peaks did we think it was? I said multiplet. I was going to say maybe less. Maybe it's 4. Is it easy to see on your sheet? That's how hard, oh, you need a sheet, sorry. That's how hard it's going to be to read on the test, too. Which is why I will not make these so hard that you have to try and guess at this kind of stuff. So coming back to it again, I do feel like it's a quartet. And if it's a quartet, that actually makes me think it's got how many neighbors? At least 3. It can't have more than 3. It could have one neighbor, it could have a CH, it could have a CH2 neighbor, it could have a CH3 neighbor, but that is as many neighbors as it can have, with the other side being a carbonyl. So shall we say it's a CH3? Because that makes the most sense. If you're following along, we have just determined the structure around the ester. The OR group is connected to a CH2, and the carbonyl is bonded to a CH2. And that's all that we've determined right now. So what we need to try and do is wrap up the chains. This is either going to be a ring. Let me pull back a little bit. We've just determined that our ester has a CH2 on one side and a CH2 on the other side. And we need to figure out, how does this molecule end on the chains? Or we have to figure out, how does this molecule wrap around? What if all of those groups come back together and connect? Do you remember the 2 chicken rule could actually help us determine that? What do you need to use the to use the two chicken rule? We either need the structure, which is what we're determining, and we can count pi bonds and rings, or we need the chemical formula so that we can plug in chicken, C, H, X, and N. And I don't have either of those. So I actually don't know whether, I feel a lot less worried, by the way. I actually don't know whether this is a linear ester or a cyclic ester at the moment. We'll just have to keep filling things in. So let's get to signal C, because signal C is the only one we haven't already made some guess about. Tell me.
Why do you have 3 CH2s right there, but only 2 on your structure over here?
This is not a CH2 that I have determined anything about.
Oh, that's a question mark.
It's in green because it's a prediction. What's in orange is what we're getting from the signal.
Oh, gotcha. Got you. So it's like that's 3, and you don't have 3.
Good point. We don't have 3. But that's just the best that our prediction is giving right now.
But if that orange CH2 needs 2 neighbors, it's fine to be bonded to the ester?
Yes. The only other way that this CH2 could have 2 neighbors is if it had one neighbor on each side, but then it couldn't be bonded to the oxygen.
Right.
And then its signal wouldn't be shifted all the way down to 4.
Okay.
It's a good question. But we actually started by saying because of its chemical shift, it must be next to the oxygen. And that takes up one of its 2 places. All right, we've got this signal C, which is a 1H multiplet. Its signal is around 1.6 according to our correlation tables. Sorry, let me show you guys the correlation table. According to our proton NMR correlation table, 1.6 is not really functional group adjacent. That's more alkane. So this CH has 3 groups coming off of it. What? How can I know that the CH signal has 3 groups coming off? It needs to get 4 bonds to the carbon. Carbon has 1 bond to hydrogen, so then there must be 3 other groups coming off. What are they? Good question. We've still got a lot of 3 H's. Hey, actually, we were just talking about having a CH that had 2 methyl groups. So maybe this is bonded to 2 of our methyl groups. The other place that it could be is, or the other thing that could be attached is this chain. This group could be connected still. Oh, I was going to say something else as well. Well, because it's a multiplet, we know the number of neighbors is greater than or equal to 4, I would say. We know that there's at least 4 neighbors. There's going to be a lot going on here. It's not connected to the carbonyl, or its signal would be shifted more left. It's not connected to the oxygen, or its signal would be shifted way more left. So it's probably connected in every direction to just carbon groups. Whatever this last group is, to be honest, the splitting patterns aren't making sense, actually. But it's got to be just a carbon chain. So I'm going to leave it as a question mark for now, but I think we have a lot of information that we can use to start plugging this in. And how many carbons have we figured? 1, 2, 3. And I've got the carbonyl carbon. I've got the carbon next to the oxygen. I've got the carbon next to the carbonyl. And then 3 more would be 1, 2, 3. All right, so we start building it from what we have. An ester with what is looking to be a lot more like a CH2. Yeah. A CH2 for sure. And then on the other side, a CH2 next to a CH3. The CH2 of the carbonyl, we felt pretty confident maybe had a CH3 bonded to it because it's got a lot of peaks, so it's got to have a lot of neighbors. Can't be the CH, which means the CH has to be over here next to this guy. Here is where our understanding of this 9H could actually be throwing us off. What if one of them is a singlet CH3? Oh, but it can't be. No, sorry, just kidding. Okay, that's the best we can predict. What I'm not happy about from this is the 2H next to the oxygen. 2H next to the oxygen is shown as a triplet, which we would expect then to have two neighbors, and it only has one neighbor. So I'm not very happy about that. What I want to show you guys now is the website where we can actually find these structures. Japanese Spectral Database, SDBS. This compound is isobutyl propionate. Let's look at the proton NMR. Hey, you know what? That looks a lot like what we just predicted, but it doesn't look like what we had. It's very close, but it is very different. So listen, I'm not sure. I make a lot of mistakes when I put the integrations on. And I wonder if I made a mistake on the integration. I have caught all the integration mistakes that are on your upcoming unit test, so you don't have to worry. I've made that mistake before, and students have really struggled. So I have updated those. Let me just check that I've updated them. I'll make a note for myself. It is, also the PLO has a mistake like that. Remember, the PLO is not my assignment, but the PLO has a mistake like that where one of the integrations is wrong. Another one on the PLO where the integration is just missing. I would say that is the challenge about taking real data, is that if I just make a mistake when I put in a number, it can't really be solved true to that. Okay, we need to figure out what this structure is then. So why don't we try doing this? We've got this triplet at 4.1. I'm going to try and use the search function that SDBS has that allows me to take a proton NMR around 4.1. It's giving me this allowance, plus or minus 0.1 ppm. It won't let me look for like what type of signals, triplet, singlet, doublet. Okay, so it gave me 1,600 hits, which is a lot. Yes, I agree, but I can actually define this more to say that I've got 1, 2, 3, at least 6, but maybe up to 8 carbons, I think that I've got 2 oxygens. If I'm wrong about the integrations, if I made a mistake there, I don't necessarily want to put in the number of hydrogens because I'm not sure that that number is actually correct. So I'm refining this with some number of carbons and this proton signal. It should limit a lot of those hits. I now only have 134. Okay, I don't believe I gave you something with an alkyne, no methoxys. Ethyl butyrate is a good idea. That is something we should investigate. That looks really similar, but not the same.
There's too many
This,
spread out around one.
the signals are too clean. That 1H that I gave you guys is very well, it's a lot cleaner than the 1H that we're seeing here. I'll bet that's the mistake. This is probably not a 1H. Okay, so we go back, return to the results, and we keep searching. I didn't give you a formate, but that would have been cool. Butyl acetate. No, too clean. Look at that singlet. Acetate has a singlet CH3 next to the carbonyl. Too clean. All right, well, if I can't find this soon, you're just gonna have to wait until I figure it out. I'll be honest. I don't know what the mistake is. It's gotta be in the integration. Nope. Nope. Butyl propanoate. I think that's it. Okay. Well, the HSP numbers are different. Shoot. Okay. A straight 4-carbon chain would have, honestly, kind of made sense. Propyl butyrate, that's not it either. Propyl isobutyrate. Oh, that's not it either. All right, well, somebody on the internet is looking at this, laughing at how we didn't get it yet. And by we, I mean laughing at me, but that's okay. I think we'll have to come back to it and try to figure out its structure once I figure out what the mistake was that I made. These have too many carbons, too many hydrogens. All right. How do you guys feel? Are you upset that I have to fail you all on this now? You are being graded on just being here right now. Oh, I found it. I missed a CH2 group. So where we see 1H, it should actually be 3H. So look at this, around 1.5, I have 2 signals, 1.7 and 1.5, and they're overlapped with each other. One of them comes from C. C is the CH. And one of them comes from D. D is the neighboring 2H. Amazing. Okay, do you want to change it? Signal C, here's the mistake. Signal C around 1.5, the one that's labeled as 1H, is not 1H. Okay, that was the mistake the whole time. Which actually makes it a lot harder to solve it because how do you get a 3H multiplet? When you see 3H, I've kind of trained you to think first think of it as a methyl group. If it's a methyl group, that means there's only one thing connected to it, only one group connected. If the group connected is a CH, then the methyl signal shows up as a doublet. If the CH3 is connected to a CH2, then the methyl group shows up as a triplet. So how do you get something ugly and messy like this multiplet? It's not a 3H. It's the overlap of a CH and a CH2. Now, when we come back with that information and we look at it, when we look at that 1H signal, oh, I see it. See the edge on the left? Peak, peak, peak. Mixture of the two signals, and then on the right, peak, peak. So there's this broad multiplet showing up from the 1H because the 1H had at least 6 neighbors. So the 1H signal is going to show up as at least 7 peaks. And then there's this nice triplet sitting right in the middle, overlapped with each other. And how do you get a triplet? Do you know what? I think it's probably actually a quartet because of how this is going to have to fit together. To get a quartet, I need 1H on one side and a CH2 on the other, which means that here I've got a CH2. So my structure was missing this CH2. Here was my signal A. Here was my signal B. These were both showing up as what I had labeled as C because they overlapped with each other. Are they identical to each other? Far from it. Do they show up in the same chemical shift? Unfortunately, yes. And then these were what I was calling D. Are they identical to each other? Far from it. Do they show up too close to differentiate? They do. Actually, now that I look at it again, I really can see the separation between the triplet CH3 and the doublet 6H on the right.
I was looking it up and I think it could also be isobutyl butyrate.
I don't.
Potentially? Do you think?
So here's what we just drew was isopentyl butyrate. Remember, iso's always got that little like peace sign at the end of it. 1, 2, 3, 4, 5 carbons, pentyl, with an iso distribution, isopentyl. And you're saying isobutyl butyrate.
It was isobutyl butyrate, yeah.
Isobutyl butyrate
Put it on the other side.
is a structural isomer. So same chemical formula, different connectivity. How would we distinguish? It's this signal, this 2H. No. It's the 2H that's in here. Oh, okay. No, I think you are right. I think it is this one. In which case, let me label. Because I said it did look like a triplet inside of that 1H, 2H. But to be a triplet, the 2H would need to have only 2 neighbors. And here, we can't have a structure unless it has 3. So here's signal A furthest to the left next to the oxygen. Here's signal B, second furthest to the left. And then signal C is the 1H and the 2H. Oh, no, you know what? This is giving it more neighbors.
Okay.
Now it has 5 neighbors, not 3. This would show up as a sextet, not a triplet. I'm not sure about this one. And then again, D, here, here, and here. I don't think it is this.
Okay.
Sorry.
No, it's okay. The NMR just looked very.
Oh, actually, I can confirm that it's not because
Number on the bottom left, right?
it's got an identifying code. HSP 0251, HSP 02517. It is the same. Yes, Gavin?
How again do we determine it's a 3H and not a 1H?
Oh,
Proceed.
because I messed up.
What determines the H again?
Integration is where we get this. Integration is where we get these numbers. Integration is a calculus term. It means everything included under the curve, the area under the curve.
Was that just based on eyeballing it? Is that how we decided that?
You didn't decide it at all. You were
Given to us.
you were given it.
And then,
I decided it because I picked the spectrum from online and then I manually added in those numbers.
what does that do for us helping us identify the chemical?
It tells you how many hydrogens produce that signal, which means if you take the integration from an NMR, you know how many hydrogens are in the molecule. Because all of the hydrogens in the molecule produce a proton NMR signal. You agree with that, Gavin?
Yeah.
So when I look at this, that's why earlier I didn't plug in the number of hydrogens into my search. When I look at this integration, 2H, 2H, 1H, 9H, I would calculate a chemical formula with 14 hydrogens, which would not have been true because the true chemical formula actually has 16 hydrogens. That can be useful if you have options of compounds and you're like, hey, these two have 16 hydrogens and these two have more or less than 16. I'm not going to consider the compounds that have more or less.
On the test, are we given a molecular formula or are we just...
Okay, so on the unit test this weekend, you're given a chemical formula and you're given the IR and the NMR spectrum. I have gone back in recent semesters. There's an image that will pop up in the quiz. You guys are used to seeing quizzes pop up in the image, and they're a little bit low quality and challenging to read. In the text of the quiz will also be a PDF document that you can download. And the PDF is much higher resolution, so you should be able to do this. Can I tell you something? Don't cheat. On the unit test, don't take that little code that you find in the bottom and plug it in and find the compound and draw the structure. And let me tell you 2 reasons why. I've just done that with this spectrum. It's giving me nothing useful. None of these are actually the NMR spectrum that we're looking at. Even these first top hits are not the structures that we're looking at. So don't blindly go in, because it's going to be so obvious to me. If this is much harder than the structures that I will have you solve. If this is the structure I'm expecting, and then you go in there and you give me an aromatic ring with an ester, that makes no sense. We didn't have a signal that was from 6 to 8, so an aromatic ring would not have made sense at all. Also, that's not going to help you do well on the midterm a week from today. You cheat on this unit test, you're cheating yourself out of a good grade on the midterm. Remember, this is why I don't put Lockdown Browser on your unit tests. It's not that I don't care if you get a bad grade on the midterm. It's that I will let you shoot yourself in the foot. It is not my job to put to keep you from shooting the gun. It's my job to show you where the safety is, right? Thank you. Thank you. Happy 4th of July. I also, to be honest, I didn't see a way to search on here on STBS for the HSP number. So there might be a way to do it. I don't know how to do it. And to be honest, I wouldn't recommend. I just would not recommend trying to take the spectra you're given and solve for it without actually going through the work. Can't recommend it. You might kill your time, yeah. What questions can I answer? What was the biggest challenge in doing this?
It's all just so confusing.
My integration was wrong. That was the biggest challenge.
Right, I was like, I felt like I got it, but the 2H was in the wrong spot.
Yep.
I realized it was
So if the integration hadn't been wrong, that process would have gone a little bit more smoothly. But can you talk more, Gavin, about what about the whole process was so confusing? This by the way, is kind of this is an interesting approach. You don't need to do this approach. You can kind of, like you can see here, I built each piece around the signal, around the information that I had. But you don't have to do that. Some people just dive in, guess and check a structure, and then start making rearrangements as they want to.
Are we gonna get like the cheat sheets on the midterm to see the spectrums and?
Let me show you what it looks like. Because you have access to the previous midterm. Here is what your previous midterm looks like. First of all, the front page gives you a periodic table. And then you get this. Is that the same correlation table as the one I handed out to you last week? Mostly. Doesn't have the words. The one that I gave you says functional group adjacent, alkane, vanillic, aryl, carboxylic acid, and aldehyde. This is your IR correlation table. Is that the same as what I gave you? Mostly. But it doesn't have the structures. Instead, it has descriptors.
It could always be changed.
It can always be changed. Yeah, I could give neither of those. So I remember there's a lot of nuance in the way that the example structures are built, which is why I give the example structures for the proton NMR correlation table. But there's less nuance. Actually, there's more nuance in the descriptors than there are in the structural drawing for the IR. So I'm leaving the component of the correlation table that gives you the most information if you understand the nuanced information. If you know how to use this tool, this is just as good a form as the one I gave you in person. If you don't know how to use this form, it's not going to matter anyways. If you don't know how to use this tool, it doesn't matter whether you have another version or less. I will not give you a carbon NMR correlation, and I will not give you a mass spec correlation because those just will not be useful. And as you can kind of see, it's already taking up a lot of space. So these are what I think you will need the most. This is what I believe will benefit you the most. Saray, you had a question?
You're not going to give us anything that will overlap.
I'll do my best not to, but as you can see, it happens. It is quite common that groups overlap. And sometimes the question might hit on that. How can a signal suggest that there are 5 protons that are identical to each other? There is no such thing as having 2.5 protons symmetric to 2.5 protons. So it's not like it's one signal of 5H. It's not like one carbon can have 5H. How can that result? Could result from the overlap of a 2H and a 3H signal. That's how that could result. So I can't guarantee that I won't give you signals that have overlapping peaks because the vast majority of molecules will have overlapping peaks.
Is the H number is it the same type of hydrogens in a certain region, or is it?
Usually,
Okay.
like when in the one we just solved, that furthest left signal is 2H, which is why I had you interpret that as a CH2 group. can you know for a fact that CH2 has a carbon? The signal is telling you H's, not carbons. But what else are they going to bond to?
Carbon.
Maybe a nitrogen, but nitrogens don't split. Hydrogens on nitrogens don't split their peaks, their signals, into peaks. So to have a splitting pattern, those two hydrogens must be attached to something, and they must be attached to a carbon. However, 3H here, which I had mistakenly written as 1H, is not 3 identical hydrogens. Although we do often look for CH3 groups, this 3H could only result from the overlap of a 1H and a 2H. So signals often have an integration corresponding to the number of identical hydrogens, but they don't always.
Just like a little question on the carbon NMR. Are the number of peaks supposed to be how many carbons are in the compound, or is it just kind of telling you where it is, so what it like should be attached to, basically?
The number of peaks in a carbon NMR inform about the number of types of carbons. But it doesn't necessarily tell you how many carbons.
Okay, so if it's like you have, you have 3 CH3s, they're not gonna show up on the same peak, or they will?
Depends. Are they identical?
Okay.
And are they the same type of carbon? Or are they different types of carbons? Then they'll show up different.
Okay.
So
there's 7.
if we labeled this as signals 1 through 7. Oh, you know what? I didn't count this one, did I? That one's at 10. I even said this one only went through 20 to 30, but actually it's more like 10 to 30. I thought that was the TMS signal, but it's not. If I label these as 1, 2, 3, 4, 5, 6, 7, 1 through 7 from left to right, and then come in here, 1 is the carbonyl carbon, 2 is the carbon by the oxygen, 3 is the carbon by the carbonyl, and then I've got 1, 2, 3, 4, 5 left, but only 1, 2, 3, 4 signals left.
So because those CH3s are identical.
Good. I don't feel confident in assigning these, to be honest. I'm gonna say 4 is probably the tertiary carbon. Tertiary things shift left. Hydrogens on tertiary carbons shift further left. Tertiary carbons shift further left. And then I'm gonna say the CH2, 5. I'm gonna say this one is 6 because it's closer to the carbonyl. And then these are both 7 because they're furthest from the carbonyl and the least substituted and identical. But you wouldn't know that any of these signals represents twice as many carbons as the others because the height means nothing and the area here is not useful.
Sorry, what were those numbers that you just went there?
If I had labeled this carbon NMR as signals 1 through 7
Oh, okay.
from left to right, these are where those signals would show up. These are the carbons those signals would come from. The carbons, not the hydrogens, because there's famously no hydrogens at that ester carbon.
Is carbon NMR going to be on the midterm? I think you already answered that.
No, it won't be. Maybe as a bonus question.
And if we make like a really good guess, but it's not correct, we still get partial credit.
Yeah, even on the test this weekend, I do give partial credit. First of all, part of your unit test is determine the structure, but annotate the IR. So you just have to go in there and you get points for just pulling out key peaks in the IR and correlating them to their bond types. Then you get partial credit for having the functional groups in your structure that you indicated from the IR. Then you get partial credit from having the actual structure. So you can definitely pass part B without the correct structure because you've gleaned the right types of information. Patrick, I feel like you had your hand raised earlier. I never called on it.
No, it was just.
You're good? Okay. Elvira?
So if you just have like a linear propane chain,
Mm-hmm.
would that only be one thing on the carbon NMR?
No,
Because you have a CH2.
it'd be 2.
Okay.
The methyl groups are identical,
And then there's one in the middle.
and the CH2 is
Okay.
itself.
So
What
you'd
ab-
never have just one, unless it was just a carbon-carbon bond?
If you analyzed methanol, that's one signal. If you analyzed ethane, they would give the same signal.
Yeah.
Even if you analyzed glycol, 1,2-ethane diol, those are identical.
Because those are just the same CH as CH2s.
Yeah, they're symmetric to each other.
Okay, cool.
How many proton signals would this give? Propane. 8 hydrogens. That would be the integration. How many signals would they show up across? 2 unique signals. A 6H triplet and a 2H septet.
Yeah.
Great. Evelyn.
For our midterm, is the cheat sheet like a small note card, or is it like a?
Thanks for asking that. Your cheat sheet is a regular sheet of paper, 8 by 11, handwritten. And I know a lot of you have tablets, and you're very good at taking your notes on tablets, but this is the only way that I can make it consistent for all students, is that you bring in a resource that is the same. So handwritten on a piece of paper, nothing printed, nothing taped on. My biochem professor allowed us to bring in cheat sheets in my biochem class in college. But he actually provided a cheat sheet, and then we could print it off ahead of time, or he handed it out in class, and we could fill in all the blank space with all our extra notes. And there were these girls that printed off a version from online, but had
Change the margin.
added all these things, just like took things, put it on, and then printed it. And he took their cheat sheets away at the start of the class.
Bummer.
Like right at the beginning of the exam, he looked down and ripped out their cheat sheets. I think they left like 15 minutes in just crying. But remember, the most useful cheat sheet is the one you don't need. If you think you can build a cheat sheet the day before and then come in and make use of it, it will probably slow you down and it will probably worsen your grade. So I would say make a cheat sheet today and then revise that cheat sheet on Saturday and then make a third revision to that cheat sheet Tuesday night before you come in. And when you come in Wednesday next week, you've gone through the material that's on there so much, you don't really need it because you know it, because you spent all that time on it.
Is it one-sided or two-sided?
One-sided for the midterm, two-sided for the final. And what a lot of students end up doing is taking the cheat sheet they made for the midterm and making a second cheat sheet for the second half of the semester, and then just bringing them both in for the final. 2 half sheets, or 2 sheets, 2 one sides of a piece of paper.
Do we get to keep it after we take these?
Please, because I don't want it. I don't need it. If you want to throw it away, that's great. I don't need it. The reason I allow it is because if you're going to go on to take the MCAT or some other type of entrance exam, I see this as your cliff notes of OChem. What was the most important stuff? What was the most challenging stuff? And when you're reviewing for OChem later, I've had former students of mine tell me their cheat sheet was a super useful resource.
Is there going to be like, you probably already answered this, like a study guide that has like all the main topics we need to study?
Rather than having that for the midterm, I've already broken it out by units. So your learning objectives on Canvas, which is the first document at the top of each module. Your learning objectives already hit on each of the main things that I want you to know for that unit.
Okay, so just look at that. And then,
If you print off your learning objectives and you go through it like a checklist, you can identify the things you know, the things you don't know, and the things you didn't know. And you can focus on the things you don't know, and the things you didn't know. So use the learning objectives as a checklist to know that you're solid on everything. Because I like to use my learning objectives when I'm building an exam. I look at it and I say, do I have too many questions that hit on this learning objective? Have I done any questions that hit on these learning objectives? And I try to make sure that my questions hit on what I asked you to learn, what I planned on teaching you. So use the learning objectives. That's your study guide. You don't need one for the midterm. You don't need one for the final. The ones from the units are better. Anything else? You guys got questions about the midterm, which is great. I'm not even like stressed about time because I've never had, mass spec is not hard. I've never had this much time to go over it either. So we've got time to kill.
Like today, you mean?
To the rest of today and tomorrow. Yeah.
Oh, and tomorrow. Oh, and tomorrow.
Yeah.
I was like, like 5 minutes.
What about next Tuesday? Do you know what's coming Tuesday? A review. We're doing a review on Tuesday. So you're going to be coming in off of the unit test. I will be opening a practice quiz Tuesday morning. It is a quiz that pulls all questions from the 3 unit tests. So it's one quiz, all questions. You guys know that on your part A's, you get like different versions of the test on each attempt. And there are questions inside of each of those learning objectives that you actually haven't seen. Because I have question banks that have 4 or 5 questions, and you've seen at most 2. So you can open that quiz, and you will get every unit test question
There is.
that there is.
It won't pull.
It won't pull, it just pulls all of them.
Okay, great.
It won't pull a select number, it'll pull all of them. Which can be a little daunting because when you start the quiz, then it's something like 900 questions. Oh, sorry, like 100 questions for the first 3 units, and then like 200 questions when I open the one for the final exam. So I would say open it and just skim through them and find the ones that you think are challenging. When you're going through the learning objectives and you're like, hey, I don't know what that even means, go open this practice test and find the questions that hit on that learning objective. So I'll open that Tuesday morning. I know that gives you a 24-hour window to actually utilize it before you come in, but I can't really open it any sooner because the Unit 3 test closes Monday night. So.
Do you think the practice question banks on active are helpful?
Yeah.
Okay.
But again, use those practice question banks on active as you need it.
Right.
I would say just go through and find the questions you need.
Yeah.
Maybe don't go through all of them because there's a lot. There's a lot. Huh? Yeah, the first few sections have over 100, and then I got feedback from students in my first few semesters teaching with active, and they were like, can you please have less than 200? Because that's too many problems for me to go through and practice. So skim through them.
Yeah. And each chapter has a follow-up too, which is helpful.
Ah, right. That follow-up publishes a few days after you finish, but allows you to go back in and see what you need to work on. What time do we meet here Wednesday next week? 10 o'clock. Get in here at 10. I'll start at 10:05 because we have 90 minutes. And so starting at 10:05 takes us to 11:35 and then class is done. So we don't really have any other time.
Do you usually have students that have a hard time finishing in that time, or?
I would say usually the lowest scoring exams are the ones that finish early and turn in early.
No, that makes sense.
I've had students that will turn in their exams in the first 30 minutes.
Oh my god.
and they don't usually do very well. Um, then again, like some of those students that really know their stuff, they leave around 45, 50 minutes, and they can get some pretty high scores. So I think the people that turn it in at 30 minutes are just saying, I've got other things I want to do with my time, and I'm not going to do any better than this anyways. No, I don't generally have students that struggle to finish in 90 minutes unless they have testing accommodations where they need that double time anyways.
How many questions?
It varies, but something like 30 to 40. There are some questions that are multi-part questions, so that changes how you read it. It's a 70-point test. If you go back and look at the practice midterms, it looks so similar to those. Almost always, I'll pick a molecule and have you just super analyze it. Sometimes it's an amino acid, sometimes it's an essential oil, but it's usually some sort of relevant organic molecule. And you go through and apply all of the terminology we've gone through. Functional groups, degrees of substitution, degrees of unsaturation, mass spec, IR, NMR, chirality, conformations, high energy, low energy, acid-base chemistry, pKa's. And it's usually just one molecule that you just analyze, which is things you guys have already done in your analysis of an organic compound. You maybe haven't done all of those things, but you've learned how to look at a molecule and answer a bunch of different questions about it.
I'll have to look at the practice ones, but is it like multiple choice or mostly free form?
It's a mixture. I would say it's 3/4 multiple choice, 1/4 short answer in terms of points. Short answer includes arrow pushing, nomenclature, writing a name and drawing a name, and ranking, generally. Arrow pushing, nomenclature, ranking. Those are the short answer questions. And on the midterm, I will not have a, oh no, just kidding, never mind.
On the other midterms, they have like bonus questions on them.
Yep.
based on this one.
Generally, up to 10% extra credit. And what I like about those bonus questions is that they often pick out what information you know about. Like, hey, you were shown a reaction up above. Name the product that was formed. None of the multiple choice questions asked you about the name, but you should know nomenclature, so show me the name. Or here's your ranking, explain it. Rationalize your ranking. Show me what you were thinking. I love those bonus questions that show me that you know more than just what the question hinted at. Because I do not give extra credit for doing something. I give extra credit for learning, for showing knowledge. So all of the bonus questions require you to show some knowledge. There can be partial credit on them too. What else?
This stuff will all be on it, right?
All spectroscopy. Yes, it will. Speaking of spectroscopy, what did we say that meant when we started talking about it last week? Spectroscopy. Yeah, spectra means a spectrum, some range. Scopy means looking at light. Telescopy, microscopy. Scopy is referring to interactions with light or viewing light, and spectra is telling us across the spectrum. Our last technique, mass spectrometry, it is not the same as NMR spectroscopy and IR spectroscopy. This is mass spectrometry. So what does the spect mean again at the start of the word? Spectrum, a range. And what does the metry mean? Measurement. Right, like other types of metry. All right. So this is actually not a type of spectroscopy because no light is involved. The setup. Are mass spec instruments. We abbreviate mass spec quite a bit as MS. They have some sort of sample input. This is most often in the gas phase. And it's a very, very small amount of sample, like hundreds of millions of molecules. Just a tiny collection. I'm always trying to evoke more of a reaction, but nobody ever seems to care when I say that hundreds of millions is a small sample. Because what is hundreds? Hundreds of millions is like 10 to the 8th, right? That's hundreds of millions. And compare that to 1 mole, 10 to the 23rd. That is a small selection. If you have a mole of water, you've got about this much water, which already looks like a small amount. That's a huge amount. So 10 to the 8th relative to the mole is 10 to the negative 15th moles. So we're taking a very small amount of sample, but statistically, the results that we get from hundreds of millions of molecules going through an analysis means that we should get repeatable results every single time, right? If I survey even 1,000 people, I can call my results significantly, statistically significant because I've got a huge sample batch, right? Okay, I'm not a stats person, so somebody out there is saying, no, that's not how that works. But I think you get what I mean. If I sample thousands of things, I've got a good sample size. If I sample hundreds of millions of things, I've got a great sample size. And we'll find that this gives us repeatable results every time. Sample input comes in a gas phase, a small number of molecules. Inside the instrument is the ionization chamber. Ooh, we're going to ionize it. How do you make an ion? Add or remove electrons. Could I remove protons instead? Yeah, I guess I could. It is hard to add protons, unless, of course, I'm literally adding hydrogen ions, which are just protons. What we're going to do here is electrons. We're going to actually pull out electrons. So our ionization chamber takes our neutral molecules and ionizes them by removing an electron. How do you remove an electron from a molecule? We will use an electron beam. I like to think of it as an electron BB gun. We shoot this electron beam at the molecule. And this electron beam has just the right energy to take an electron off of my molecule and eject one of them. Okay, M molecule.
Is that affecting the whole sample or just?
Molecule by molecule. But you're right, all of those molecules that are being put in there are each having an electron picked off of them. And again, like, I think of this like a BB gun on a log, or shooting cans off a log. You're just firing them off.
Well, what happens to ejected electrons? Do you just like find a new home or something?
Well, that's a good question. What about the beam of electrons? Where are they going? How do you even generate a beam of electrons? So we've got a part of our instrument here that pushes energy into a metal sample that can then eject those electrons because of that high energy. And those electrons are being pulled towards another part of the instrument that accepts electrons. And then, of course, the energy from those accepted electrons we can create a cycle here. So those ejected electrons are going to go to the same place that the electron beam goes to.
Is that like magnets, like a tube, or like a plate?
Cathodes, which are magnets and tubes, basically. Yeah, more in the weeds than we need to be. So, Ray?
Would the electrons from the electron beam, would they be high energy electrons, or would they just be
There's a weird relationship between electrons and their energy and the character of electrons and their energy. Low energy electrons don't do much to a molecule. Around 70 electron volts, they can do a lot of things to a molecule. They can pull out electrons from the deepest part of an atom. And then high energy electrons, again, don't do much to a molecule. So there's kind of this sweet spot, depending on what you want to do to a molecule. Do you want to eject one of the core electrons? You actually would use like this sweet spot in the middle. Do you want to eject not a core electron, but like an outer layer electron? You could use either range outside of that. So they're kind of high energy, but they're not necessarily super high energy. What happens after an electron is removed? My molecule now has a positive charge. It's a cation. Why? Because I just lost an electron, so my balance of positive and negative charges is now missing. Plus, in my molecule, every electron was paired, and now I will have lost the pair to one of my electrons. So it is also a radical. So the instrumental setup starts like this. My molecule is input into the instrument where it's ionized by an electron beam to form a radical and a cation. Good with that? Quinn?
It's called a radical because it lost a lone pair. Is that what it's called? That?
No.
No.
It's called a radical because it has an unpaired electrons. I agree that it looks like I've taken a lone pair electron, but I just didn't have any other way of showing electrons. So I showed two. But those could be 2 electrons in a pi bond, 2 electrons in a sigma bond, 2 electrons on a lone pair. But every electron had a pair. One electron has just been ripped away from the molecule, which means that there's now one electron whose pair has just been removed. So now there's an unpaired electron, a radical. Good. The next thing that happens inside our instrument is that this molecule interacts with an electron, interacts with a magnetic field. And this brings it down to a detector. I'm always trying to improve my analogy here, so I'm going to try for one. This magnetic field interacts with the charged particle, the molecule that now has the cation, because magnetic fields interact with charged particles. So I can make this charged particle change its behavior in a magnetic field. If this structure is heavy, then the magnetic field has a hard time changing the momentum of that heavy particle. But if this structure is light, if it is not very heavy, then the same magnetic field can change its momentum a lot quicker. Think of that like using the same amount of energy to swing a tennis ball on a rope versus swinging a bowling ball on a rope. Using the same amount of energy, your tennis ball is completely in circles and the bowling ball is like next to the ground, right? Because it's harder to move a heavier thing using the same amount of force. So our detector, if it picks up a reading over here, then it knows that what hit it was heavy massed. And if it picks up a reading over here, it knows that what hit it was a light mass. And this is a lie that I find useful in understanding how it can differentiate heavy from weak. What it actually does is it spans a strength of magnetic fields. It starts with a very small magnetic field, and then it goes to a very strong magnetic field. And at a very small magnetic field, only light things hit the detector. At a very strong magnetic field, only heavy things hit the detector. But I like to think of what it would look like if all of them could be pulled towards the detector at the same time. The instrument knows when it's being hit by something heavy, when it's being hit by something light. In fact, it knows exactly the atomic mass. It's not a balance, it's not a scale, but it knows the atomic mass because of the force of the magnetic field and when it gets hit by the detector, or when that fragment hits the detector. Okay, so positively charged things get pulled to the detector, but radicals aren't affected by the magnetic field. So these samples are flying in a straight shot, and then they lose an electron, they become charged, and then they enter a magnetic field. But if they don't have a charge, what happens if they don't lose an electron? They don't get a charge. What happens if they don't have the positive charge? What if they're just a radical? They don't get affected by that magnetic field, and they just fly straight to the detector. They fly straight through past the detector. And this entire thing is happening under vacuum. So all those other fragments, they just go to the waste. They go into the vacuum. Radicals, not affected. Cations are affected. All right, I've got 30 seconds, and I'm going to not try and explain all of the little details. What we're going to look at tomorrow is, well, first of all, we always look at the spectrum. So we'll look at what the spectrum looks like and how we analyze it. We're going to look at the molecular ion, and then we're going to look at the daughter ions. Or as we said in lab yesterday, the mother ion, as opposed to the molecular ion versus the daughter ions. All right. Thank you, guys. See you tomorrow. Enjoy the rest of your day.